Bismillahirrahmanirrahim. Assalamu alaikum dear students. I am Arif and I welcome you all to lecture number 23 on the subject of computer organization and assembly language programming. The title of today's session is Data Path of Hack CPU Part 2. Well, today's session is a continuation of the previous session in which we talked as to how information flows among different components of a computer system in general. And today we will dive deep and will design the hack CPU with its data path. Well, we will start with the review of hack computer architecture. We will see the hack CPU interface and we'll see in general as to how instructions are executed by the hack CPU. We will see the hack CPU implementation, how the A and C instructions are handled, how the inputs, outputs and operations of hack ALU are managed, and finally we will see the control logic of the hack CPU and its implementation. So we have a lot to do today, so let's start playing. Well dear students, before we start with the design of the hack CPU, let us have a quick recap of the overall hack computer architecture. Well, our hack computer is a 16-bit von Neumann machine designed to execute programs written in the hack machine language. It consists of a CPU and two separate memory modules serving as instruction memory and data memory, and two memory mapped I/O devices, a screen and a keyboard. Well, this hack computer executes programs that resides in this instruction memory that can be implemented using a ROM chip that is preloaded with the required program. The hack CPU consists of an ALU, and this ALU chip we have designed in lecture number 8 and 9 that is capable of performing 18 different arithmetic and logic operations depending on 6 control inputs. This hack CPU also contains 3 16-bit registers D, A and PC that we have designed in lecture number 11 and 13. Well, this program counter points to the next instruction to be executed. This D register is used solely for storing data values, and the A register serves 3 different purposes depending on the context in which it is used. Storing data value, pointing at an address inside the data memory, and pointing at an address inside the instruction memory. Well, what we need to design today is the control unit. That is how the instruction word and data word get inside the CPU, how the ALU is instructed to carry out the required operation on the data words, how the result is later written back to some appropriate address in data memory, and how the address of the next instruction is sent to the instruction memory. So actually we need to design the data path and how to control the flow of information between different components within this central processing unit. So dear students, this slide shows the hack CPU interface. At the right bottom over here, this shows the overall hack architecture, and we have to remember that this CPU does not work in isolation. It is connected to other devices inside the computer, especially the hack CPU is connected to both the instruction memory as well as the data memory. Now if you observe the hack CPU interface over here, you can see that it has 3 inputs coming from 3 completely different sources. First of all, this 16-bit data value named in M is coming from the data memory or RAM unit. and this is the value on which the CPU is going to operate on. Second is this 16-bit instruction value named instruction coming from the instruction memory or ROM unit, and this is the value which will instruct the CPU what to do. Dear students, also note that at any given point of time there is always a selected register inside this data memory, and there is always a selected register inside this instruction memory, which is mentioned by mnemonic M in hack assembly. Well, anyway, the third input to this hack CPU is a single bit input named reset, which is sort of a restarting signal. Okay, now let's talk about the four outputs of hack CPU. Well, these first three outputs deal with the result of the computation that needs to be written somewhere in data memory. This first 16-bit data value named outM contains the results generated by the ALU. This second output is a single bit output named writeM, which is a load bit that enables the data memory for the write operations. This third output is the 15-bit address to the data memory. So these three outputs together decides the output of the ALU should be written to what address of the data memory, and this is the write enable bit of the data memory. In addition to these three outputs, there is an extremely important 15-bit output named PC, program counter, and this output is the address of the next instruction that has to be fetched and executed in the next cycle of this computer. Well, dear students, before we move ahead and discuss the implementation of hack CPU chip, let us understand how the A and the C instructions get executed by this hack CPU by taking some examples. And the first example is D is equal to D minus A. So this is the hack assembly format. Well, it says the ALU, this ALU will read the data from the D and the A register, and the result is also written inside the D register. So in this case, neither the memory is read from the in M input of the CPU, nor the memory is written by the out M, write M, and the address M output of the CPU. Let's see another instruction, at 17. Well, the value 17 is stored in the A register, and this value is also emitted by the 15-bit address M output over here. This is what add 17 will do. For M is equal to D instruction, since the left hand side includes M, so we need to write the data memory. Therefore, the ALU output is emitted by out M, and the write M bit will also be set to 1. And for D is equal to M plus 1 instruction, since this right hand side now includes M, so we need to read data memory from in M of the CPU interface. So you have a fair idea how these inputs and outputs of hack CPU can work in coordination together. Let us understand this reset bit and this 15-bit output named PC as well. Well, dear students, if this reset bit is set to 1, the 15-bit output PC emits 0. So we have a 0 over here. So this caused the program to restart. And if we have our 0 at the reset, the CPU logic uses the instructions jump bits and the ALU's output together to decide if there should be a jump or not. For example, consider this set of instructions: at 54, D minus 1, jump if equal. So this 54 will be placed in this A register. This computation D minus 1 will be performed by the ALU, and if it outputs 0, then PC is set to the value inside the A register, that is a jump will be performed. And if this condition is false, then we will do PC plus plus, and the final updated PC value is emitted by 15-bit output named PC over here. Okay, so dear students, this is the proposed implementation of the functionality of hack CPU that I have just described on the previous slide. This is one way of doing it as designed by Norm and Shimon. There can be other ways as well. Before diving into the details, let us look at the interface of this hardware diagram. And it is 100% identical to what we have seen on previous slide. On the left hand side, you can see the 16-bit instruction coming from the instruction memory, 16-bit in M coming from the data memory, and the single bit reset input. On the right hand side, you can see the 16-bit output named out M, single bit write M, and 15-bit address M. And these three outputs are for writing the result inside the data memory. Moreover, you can see the 15-bit output PC as well that I have described on the previous slide. Now let us have a bird's eye view of different components inside our hack CPU. Well, as you can see, there are three registers: the A register, the D register, and the PC. There are two MUX16 chips that we have designed in lecture number 5, I think. Here these multiplexers are used to decide about the input of the A register and the ALU. This MUX16 chip is going to decide whether this A register will be loaded from the output of the ALU or maybe from the instruction part. This ALU chip over here, you can see it has been designed in lecture number 8 and 9 of this course, I think. So we have registers, we have multiplexers, and we have the ALU chip. And with all these components, you can see different control inputs represented by C's. You can see different control inputs which are shown by C over here. These are single bit inputs, and these are multi-bit inputs, and this is output as well, multi-bit output, control output of ALU. Dear students, these control inputs together will cause the CPU to do what it is supposed to do at a particular instant of time. So now, after having a fair idea about how different elements or components within the CPU are connected with each other, let's start with the section that deals with the current instruction. Well, over here you can see the 16-bit instruction coming inside the CPU. And we all know that the hack CPU supports two types of instructions, the A instruction and the C instructions. And let us take these two types one by one. So zooming this section, show that it consists of mainly the A register, and the instruction input connects to this register via this multiplexer MUX16 chip. Let us suppose that the instruction coming in is an A instruction, symbolically written as at 5, and the 16-bit binary encoding is also shown over here. Dear students, we all know that this most significant bit of the hack instruction decides about the type of the instruction. So over here it is 0, so that means this is an A instruction. Moreover, also note that this 15th bit, most significant bit of the instruction, is also placed at the select input of this MUX16 chip. And since this is a 0, so the remaining 15 bits, that is the data value over here, which is 5, is placed inside the A register. And this is what an A instruction is supposed to do. So this is a summary as to how the CPU handles the A instruction. And one more thing, there is the content of A register are also sent to the ALU via another MUX that is not shown over here. One more point that I want to mention over here or emphasize over here is that in case of an A instruction, this A register gets its input from the instruction part, and in case if this is a C instruction, the A register will get its input from the output of the ALU. So now let us see how the C instruction is handled. Well, consider this hypothetical C instruction. From this symbolic code of the instruction, we can see the three parts colored differently for just for understanding purpose. The destination is the D register, the computation is D+1, and we have an unconditional jump as well. And this is a 16-bit binary encoding of the same instruction. The most significant bit of this instruction is 1, so the CPU knows that this is a C instruction. This bit number 15 will be placed at the select input of this MUX16 chip. So in case of a C instruction, this A register will be fed from the ALU output like this. So this is how the CPU handles the 4 parts of a C instruction. First of all, the most significant bit decides the type of the instruction and is fed to the select input of the MUX16 chip. The next 2 bits are shown in white over here are reserve or spare. They do nothing. They means nothing. The next 7 bits shown in blue decides which arithmetic or logic operation the ALU need to perform. So these are the control inputs of the ALU, and this combination of bits will instruct the ALU to do a D+1 operation. So these 6 bits over here represents a D+1 operation. Well, the next 3 bits shown in green are the destination bits, and this combination of 0, 1, 0 means load the D register. And finally the last 3 bits shown in red are the jump bits, and all ones means an unconditional jump. Now the task of the CPU designer is to route these bits to control inputs of appropriate chip part destinations, and these control inputs are labeled C with every component on this slide as well. Okay, so now is the time to discuss the ALU operation, which is by far the most complex part of this architecture, I think. So this is a segment, highlighted segment that deals with the ALU, and we all know that this ALU is a combinational chip. And by a combinational chip, I mean it always computes something. There are always some inputs coming in, and there is always some output going out. Well, dear students, let us now consider a C instruction that is coming in. And we all know that C instruction consists of different or fields of bits, each of which has a specific meaning. You can observe over here that the inputs to the ALU are coming from two different sources. One of them is from the current value of the D register, and the other one is either the current value of this A register or the 16-bit value from the data memory named INM. And there is a MUX16 chip which is going to decide as to where to take the value from. This MUX16 chip will decide whether to take the value from the A register or the memory. And the control bit of this multiplexer is bit number 12 of the C instruction. Bit number 12, this 0 of the C instruction. And probably we have called it A in the previous sessions. Okay, dear students, now ALU has the two inputs. The $100 question is, how does the ALU know what to do? Well, the ALU know this from the 6 control inputs. The 6 control inputs also shown over here with all C's and shown over here with this 0, 11, 1, 1 and 1. I think these are the bits shown over here. Bit numbers 6 to 11 of the instruction. So ALU know this from what to do from these 6 control inputs which specify the operation the ALU needs to perform, and these have been named probably as ZX, NX, ZY, NY, F and NO in the previous session of the ALU. Now these bits are taken from the instructions from bit number 6 to 11, represented by 6 C's over here in blue color. So the CPU designer has to take these 6 bits from the instruction and feed them over here to the ALU. Okay, now we have the 2 inputs to the ALU, and we know the operation that the ALU need to perform, and we also have the output. And the next question is, this output needs to be written where? Well, dear students, the output of the ALU is simultaneously fed into 3 different destinations. And the first destination is this D register. The second destination is this A register, and of course the third destination is outside this chip to the memory. So the ALU output is fanned out into 3 different places, knocking on 3 different doors. And now the programmer has to decide which door has to be opened, and this decision will be taken by the destination field of the instruction, shown in green over here. And over here it is 010, which means the D register. And we have seen in the previous lectures that a 000 over here, a 000 in the destination bit means don't save the ALU output in any destination. And a 111 in the destination bit means simultaneously save the ALU output in all the 3 destinations, in the memory, in the D register as well as inside the A register. Okay, dear students, now that we know as to how this 16-bit output over here of the ALU is generated based on these 6 control bits, and we also know its destination based on the 3 destination bits of the instruction. Let us also try to understand as how the 2 control outputs are produced by the ALU. If you recall, the ALU also produced 2 single bit outputs. One is the NG bit or the negative flag, which is set by the ALU if the 16-bit output is negative. The other is the ZR bit or the 0 flag, which is set by the ALU if the 16-bit output is 0. Well, dear students, these two single-bit outputs play a key role in the control logic of the CPU. And before we talk about this, let me revise the functionality of this reset input of the CPU as well. Well, this slide shows the possible outside view of our hack computer, and this is the reset button. It might look like this, and if our computer is executing a program, then pushing this this reset button will cause the program to restart its execution from the very beginning. Now let us understand the control logic of the CPU. Let us consider this schematic C instruction having different fields, and when we talk about control, we need to concentrate on these three jump bits. These three jump bits represented by J over here. And remember, this table shows the 8 possible values that these 3 bits can take. For example, our 000 means no jump, and our 111 means an unconditional jump. And rest of the 6 combinations means jump if output is maybe greater than 0 or is equal to 0, is greater than equal to 0, and so on. Now this jump to some address of the instruction memory is done by this register called the PC or the program counter, and this will always emit the address of the next instruction to be executed by the CPU. Well, dear students, if you want to start or restart your program, you need to set the program counter to a value of 0. That is, you want to execute the first instruction in your program. If these 3 bits are 0, that is, there is no jump, the program counter is just incremented by 1, assuming that the next instruction in the sequence is on the next address. So if the value of the program counter right now is 0, it will become 1, then 2, then 3, then 4, then 5, and so on. So our program will execute in a sequence. If the J bits, if all the J bits over here, all of them are 1, 1, 1, 1, so that means an unconditional jump. So this is an unconditional go-to situation. The program counter will be loaded by the value inside the A register coming from here. And the programmer must have placed the required address of the instruction memory inside the A register before this C instruction of jump. And finally, we have a conditional go-to, in which case the CPU will perform any of the 6 comparison operations shown over here in this table, and if that condition is true, the contents of A register will be placed inside the program counter, and otherwise the program counter is just incremented by 1. Well, dear students, this is how the program counter works in almost all computers. So what is left now is how we can make this happen. Okay, to start the program, we need just to push the reset button. So if the reset input of the CPU is 1, the program counter is set to 0 over here, and the already loaded program starts its execution from its very first instruction. But if the reset button is not 1, then we have to check the current instruction. Now we have to perform a function. If the jump bits are all 0, that means there is no jump, so this function returns 0. If the jump bits are all 1, so that means this is the unconditional jump, so this function will return 1. And for the rest of the 6 combination of jump bits, we will also check the ALU control outputs as well. And if the condition becomes true, this function returns 1 inside load, otherwise it returns 0. So after this line, the load bit will either have a value of 1 or 0, and this is the load bit of the program counter. Excuse me. So finally, if the load has been set to 1, that means place the contents of A register inside PC, that is jump, otherwise PC++, that is execute the next instruction in sequence. Okay, so dear students, this finally wraps up the hack CPU implementation and its data path. I have tried my best to make it simple for you. If you have not understood it in the first go, I will request rewind the video and watch it again. So that is it. All that remains is actually now to build it, and we will inshallah do that in the next lecture. I hope today's session was informative for you all. If you have liked it, please subscribe my YouTube channel and share it with your friends. I wish you all the best, happy learning, and Allah Hafiz.